All right, welcome everybody. I see folks are starting to log in. So welcome to Ask Mayfield Anything. For our discussion today, we're going to be getting into talking about transformers and applications within solar and energy storage applications. So see if folks are logging in. So as you're doing that, just want to thank you for taking the time to join us today. And then also, as we're going along, we very much encourage people to put in questions, ask what's going on, what you want to hear from the panelists, especially. And as you're doing that, if you could put those in the Q&A section. So there's both a chat and a Q&A, but if you use the Q&A section, it's much easier for us to monitor those and be able to make sure that we get through them. And there were some questions that actually came in ahead of time as well. So you're always welcome to do that during our AMA sessions. And so we'll kind of address those questions throughout. And I think we found a good way of integrating those questions that came in ahead of time. So again, thanks very much for taking the time to join us. So for those of you maybe I haven't met before, my name is Ryan Mayfield, founder of Mayfield Renewables, and been working in the industry since '99 now, and really enjoy doing these presentations, working with very smart folks out there in the industry to talk about topics that are very timely and important for our industry. Mayfield Renewables, we are a engineering consultancy. We also do a lot of education. And so as part of that is things like this AMA series. We've been doing it for nearly 44 plus years now. And being able to present these types of topics to the industry is very helpful for us. We're constantly learning, and so enjoy doing that with folks as well. So we work with EPCs, manufacturers on a variety of topics. So happy to speak with folks as you're interested in learning more about our services and how we might be able to support you. So trying to get into this is going to be a big topic. I know that we're going to be running up against the end of the hour here before we know it. So I want to jump in, introduce our two main guests here that we have today. First off, we have Jeff Somerville, Director of Technical Solutions, Hammond Power Solutions. So Hammond being a transformer manufacturer, they provide a lot of services around that. And so, Jeff, if you wouldn't mind taking a second to introduce yourself to the audience.
Sure. Thanks, Ryan, for handing it off there. Yeah, Hammond Power Solutions, if you're not familiar with us, we're the largest STRI-type transformer manufacturer in North America. Build everything from something as small and simple as a control transformer up to a 34 MVA power transformer and everything in between. So I also have with me Nick Conan, who's our application specialist, specifically around PV battery storage and other renewables. So he is also with us today to address some of the more specific things related to some of the unique requirements that come into both battery storage and the PV applications.
Perfect. Thanks, Jeff. And then we also have Medina Maric, Director of Power Systems Engineering from Dynapower. And Dynapower is, folks may know, large. They work in a lot of industries. They are, on the power conversion side, and so, but they are working a lot of energy storage and things like that. And so, wanted to bring Medina on for kind of that aspect, and when we're talking about that. So, Medina, would you mind introducing yourself as well to the group? Oh, you're muted still.
Thank you, Ryan.
There you go.
My name is Medina Maric. I'm Director of Electrical Engineering Group for Power Systems at Dynapower Company, LLC. We are located in Vermont, close to Canadian border. The company has been established in 1963 with acquisition of Rapid Power that was established in 1946. Has been around for decades, and we do have a very huge customer base and application base. We've been in power conversion industry all along, and my personal expertise lies in mainly power conversion, large rectifier systems that are utilizing thyristor technology, IGBT technologies. We do cover a variety of products, and very large presence we do have in renewable energy markets, and that's the product, and that's the area of expertise that Dynapower has been developing for slightly over 20 years. Our presence is in inverter section, in microgrids, in e-mobility, hydrogen. We also have a huge presence in defense. And I will be speaking on behalf of transformer selection for all these markets. And again, with the stress on my expertise lying in more large power conversion equipment. That is actually very similar. Along with me here is Blair Reynolds, and Blair is actually our Director of Renewables and E-Mobility for Clean Energy Engineering Group here. And Blair, if you want to say a few words, please go ahead. I'll just also mention that I've been in this industry for quite a long time, and I've also been serving in some of the heavy industries and on a different side from power conversion on user end as well. Blair, go ahead.
Thank you so much, Medina. I'm really happy to be here with another Ask Mayfield Anything. Really enjoy these. Thanks.
Great. Thanks both Blair and Medina. And so, yeah, as we're going through, both Jeff and Medina were wanting to make sure that they had the right support group. And so definitely we're getting a lot of great voices here as we've gone through in our prep sessions on these. Really excited to kind of get going on talking about the transformers. So today we're going to really focus in on, transformer configuration, PV and energy storage projects. And so, kind of want to just set that stage of there's a lot that's going through it in our prep calls. I think I'm going to paraphrase something Medina said. She said it very, very well. Is transformers are they're they've been a technology we've been using for a long, long time. Over 100 years, and seemingly something that's people take for granted or seemingly simple within the systems. And then once we start really digging into things, that they're anything but. And so this is a topic we've been receiving a lot of questions on from our own clients. And so trying to put together more and more education around it, because it's obviously a topic that is important for folks all around. So today we're going to, put a focus in on kind of, again, the PV interconnections of the applications for our PV interconnections. So an example that we see very often are doing a grid direct PV system where the inverter outputs 480, but we're connecting to a 208 utility grid. So what are the requirements around that? How should we be thinking about that? So we're going to talk about some of those big main topics, and then talking about the isolation and other requirements for energy storage systems. And so those are going to be kind of the two big things. There's a lot of other topics that we could get into, grounding transformers, things like that. We're just not going to have enough time today. And so, as I mentioned, we had some questions that came up prior to the start of the webinar. And so we're going to try and hit on those. And so I'm just going to throw them out there because I see that some of the folks that put those questions are here now. And so one of the big ones is that second bullet point is the need for energy storage and isolation transformers. So I was, Blake Gleason is somebody who has been in the industry for a long time. He sent a question along those lines. And so I really appreciate that question, Blake, and made me really appreciate that when somebody, one of, if not the smartest person in the room is asking these types of questions. It's, an important thing that we need to address and we need to talk about. So that's one. Talking about the different types of connections, Delta and Y connections or YY connections on our transformers. So we got a handful of questions talking about my utility requires a Y to Y transformer, and understanding the pros and cons or what the differences on that would be versus a Delta to Y. So touch on that. A handful of questions came in about 240 volt high leg. And so we're going to try and touch on that. It's a pretty probably could be a pretty big topic. So we will definitely talk about it and touch on that as something. And then the use of auto transformers. So all of those things, kind of the questions that came in ahead of time were kind of fell into those kind of buckets. So as we're going along, we're definitely going to hit on those. But again, questions are definitely welcome from those of you out in the audience on any of these topics. So let's jump into it. And so, Jeff, I can kind of have you take a little bit lead here. And so, kind of talking about, again, we're going to start with those grid direct PV systems and talking about, how we configure the transformers. And, I think one of the big things starting off is, that primary versus secondary talk on the transformers themselves.
Sure. That's some of these things are some of the points that are often confused in the topic of transformers. So just a couple of things from a basic standpoint to get started off. Primary and secondary, those terms really have to do with the way the transformer is designed based on some of the unique characteristics of a transformer. A transformer has to basically flux up when it's initially powered up. So as a company designing transformers, the primary side is the side that really the energy is flowing from or into rather. So you can almost think of it like a line and a load side. What's the load side of it? And the line side is the primary side, load side is the secondary. Sometimes people will look at that and think of it a lot of times as most transformers are what they call step down transformers. So it's going from a higher voltage to a lower voltage. So for instance, from 480 down to 120 or 208. And they will say 480 is the primary, 120, 208 is the secondary. Well, not necessarily. It is that would be a step down configuration, but transformers can also be designed in a step up application where they would be going, for instance, from a 208 up to a 480. So primary and secondary really don't have necessarily to do with the high voltage and the low voltage side. It's more around what side is initially energized for the transformer. So that's one important distinction there to understand. So as far as how that is typically configured in a PV system, that's why I have Nick Conan on the line with us as our application specialist. He can get a little bit more into what the typicals are for a PV, but I just wanted to make sure that everyone kind of understands difference between primary and secondary and high voltage and low voltage side. So Nick, can you?
Yep, thank you for that, Jeff. So yeah, kind of reiterating what he was saying there, what it really boils down to us is what side are you initially energizing? And once that core has been magnetized, then you are suitable for bidirectional use. So for most utility interactive applications, you're looking at that grid side energizing the primary from its primary or outer winding. Once that core is magnetized, it will usually then go on and give the inverters the signal that the grid is there and present. And once that happens, then power will flow and push back towards the grid. That's the kind of the main principle of it for grid side versus inverter side of the transformer here.
And we'll show you something else too here in a minute, and how our solar design transformers are specifically labeled as such, but the bidirectional functionality is not something that's automatic either. So in other words, not all transformers are designed for bidirectional usage. So that's an important designation there in these type systems.
Perfect. Yeah. And so, so the question came in, just want to make sure we're absolutely clear. So in I'll put air quotes around a typical PV grid direct system, we have a 480 volt inverter, we have a 208 volts utility interconnection. And so in that case, the 208 side would be the primary, the 480 would be the secondary in the eyes of the transformer, and how you're going to energize those windings and how you're going to make those connections.
Yep, yeah, that's the correct understanding there. And the nameplating too on the transformer will reflect that as well for calling out the grid side.
Perfect. Great. And so, so that's kind of the, talking about primary, secondaries. I know that gets used a lot. I mean, we've talked about it here internally ourselves. And so that's a really good one. I guess the other thing that I'd like to touch on, and there was actually a question that came up on this one already around the sizing of the transformers. So we talked about that. So I guess, Jeff, is that something you can address? Just kind of sizing the transformer with relation to, say, the PV system or the inverter output itself.
Nick, I think you had a comment on that when we were going through it as well. So you want to address that?
Sure. So all of our transformers are suitable and rated for 100% continuous duty. So generally speaking, you don't have to put in a buffer to the transformer. Oftentimes, what buffer kind of happens is the next standard size up transformer, say a 100 kilowatt array, you could go next standard size up of that 112.5 kVA. Most times, you will have off times where the array isn't producing either maximum power or maybe it's nighttime, and the transformer is more than suitable again for that 100% continuous duty.
Perfect. And then a question that came up was around oversizing for harmonics. Is that something that's necessary, Nick?
Usually when harmonics come into play, that's around when we get the best inverters, and
Okay.
it's not exactly oversizing, but we'll often put, say, like a K factor on the transformer, like a K factor 4 or 13 to be able to withstand those harmonics. But in principle, yes, it basically is oversizing the transformer to withstand the harmonics, which is, we usually just address by a K factor on the transformer.
So if you're not, if the folks on the call aren't familiar with K ratings, it's it's basically an IEEE standard that has to do with utilizing transformers in a system where harmonics are present, and there's a scale in there that is the K scale that basically goes from K1 up through K20, and the higher the number, that means the amount of harmonics, the more harmonics are present as the number goes higher. And there's actually several things that are different about the transformer to help it manage those high harmonic environments. It doesn't do anything to reduce harmonics. It just, the transformer is designed to be able to perform under its labeled load, even when harmonics are present in the system, because the harmonics in the system are kind of create a more loading on the transformer than it would be in a system without harmonics. So you could oversize the transformer, but there's some things that are not going to be adequate really for the harmonic content, even by doing that, like the rating of the neutral and then electrostatic shield and other things that just help the transformer to perform like it would in a normal environment, even with high harmonics.
If I may add to that, Jeff, harmonic content has to be taken in account with power conversion equipment. If you're dealing with thyristor rectifiers or even IGBT solutions and large systems, as Dynapower is dealing with, and you are absolutely right. We do have a lot of switching elements in our configurations, and lower the number of pulses that we are producing on DC, higher the harmonic content. And that harmonic content is defined by IEEE 519, and there are recommendations in terms of the transformers. Depending on the group and selection of the transformer and complexity, K factor goes very high. So basically with thyristor rectifiers, the minimum K factor will start from 4 and going up. In general, it will be around 13, and there are some ways of mitigating harmonics and actually making it easier for the transformer and not having generating those transformers to throw them back in the grid.
Wonderful. Great. Thank you. Thank you for all that. That's super helpful information. And then the last one on this slide, the overcurrent protection device. There was actually a first question that came in from Chris LaForge, asking about requirements around that. We're probably not going to get too far into it. Chris, one of the things I would point out to is, 705 and 450 both have overcurrent requirements for transformers. And actually gets pointed back into 240.21c as well. So also kind of a, not so shameless plug, but also this is something, a topic we talk about in our code class around PV systems as well. So I can get much more information on that, but that's definitely something to consider. Overcurrent protection really is a requirement when you start digging into NEC on both the primary and secondary side for these applications, and having those disconnecting means as well. So definitely a topic in of itself that we could dive into even further in a different topic. Okay. So let's talk a little bit about Wye and Delta configurations. And this is one where I'd love to jump into that, one of those early questions, having a Wye connection versus a Delta Y connection. So I guess first off, if we could start off with this, what I would call the standard type of connection, if we are thinking about those same grid direct PV systems where we have a 480 volt inverter, 480 volt inverter going to a 208 system. Sorry, I realize that I'm using the wrong analogy in this this way this picture shown. So very often we would have a in a non-PV system, we would have what Jeff was describing there, that step down transformer. So Jeff, can you Jeff and or Nick kind of talk to us about the Delta Y configuration and how that's being used and kind of the why we're using that type of configuration?
Sure. Let me. I just wanted to address kind of a basic thing in terms of this sort of ties into an isolation type of system first. So, regardless of what those two vector configurations are, another point that is often confused is the difference between or what exactly is an isolation transformer, and then autotransformers were mentioned as well. So basically, there's multiple functions of an isolation transformer, but what it essentially means is that the primary and secondary have a galvanic isolation between the two. So in other words, it's not a straight electrical connection. It's actually a coupled connection magnetically. So there's some inherent things to that from a safety standpoint. It is an isolation transformer is a current limiting device. And I believe, Medina, when you get into some of the things on the rectifiers and the battery storage systems, that'll come up a little bit more. But sometimes, even if it's a 480 to 480, if it's providing that isolation, it does protect the system. So that's important. It also gives you the opportunity, as you're seeing here, like on the Delta Y, to have a separately derived neutral. So it isolates the two systems there. So the term isolation transformer is confused a lot of times on really what that means. An auto transformer is just basically straight through windings, and based on where it's tapped off of, you'll have a voltage change, but there's no isolation there. So the current limiting function and the protection there is not really there. We historically had seen, let's say 10 years ago or so, quite a few people that would use auto transformers regularly just to tweak the voltage on the output of some sort of inverter, which essentially functions, but you don't get the safety that you do with an isolation transformer. So we don't see that a whole lot these days. So as far as the Delta and the Y and tying into the utility and the inverter side, Nick, can you express a little bit of what you've seen on that?
Yeah, absolutely. So again, the most common setup we'll see is the Delta facing the utility side with the Y side on the inverter side. In battery storage, it just flip-flop it around a little bit there, where often the BESS wants to be an ungrounded system. So typically it's a Delta facing the BESS side. And then with an absence of the grid only being powered by the BESS, it's good then to have that Y neutral there on that grid facing side to provide those single phase loads. Functionally for the transformer, usually in your PV applications, you only really need that Delta there on that grid facing side. Touching back on what Jeff was saying there, that with it being an isolation transformer, it creates a new separately derived neutral on that inverter facing side for that balanced reference there that the inverters like to see, or typically the PV inverters like to see. We certainly can do YY, if you have a utility that really wants to see Ys on both. That definitely is a possibility though. We do see sometimes that can cause some issues though with the neutral on the utility side there. If it is bonded as well, it often can act as a return path for neutral flux. So sometimes that has caused some heating problems in the neutral as well. So functionally, we prefer to go with the Delta there on the grid side.
Yeah, and that's been as far as when we're talking again straight grid type PV, not energy storage at this point. But if we're talking about that, it's been the Delta on the utility side, the Y on the PV side. Not every inverter requires that neutral. You can install some inverters without the neutral, but what we've been seeing is those deltas on the utility side are typically what we're speccing in, how we're engineering things. And I guess, Nick, if you could comment a little bit about why would a utility want to see a YY on both sides?
Honestly, I don't have the greatest answer to hear
Okay.
on that one. I'm more of the guy who kind of picks these single lines and sees that. But I do see a common, usually it's kind of more in geographical locations where there's a preference to utility for the Y there. If anything, it can cause problems again with the neutral flux there coming back through the neutral of our transformer. But I could see it though in the battery storage type applications where without the presence of the utility, you do need to have something to establish a neutral on the grid side.
Yeah, absolutely. And so if you are, and then we're about to get into the energy storage stuff, and but yeah, having, especially if you are, well, if you're supplying single phase loads, then you absolutely need that neutral. And if when the utility is gone, then the energy storage system is that grid. It is the, you know, what's giving us that waveform and giving us the that voltage and current to do that. So that's great. And so yeah, and so then you guys had mentioned, you know, kind of the separately derived neutrals and things like that. And so really this, you know, once we put in these isolation transformers, we are, you know, creating these separately derived systems, and we need to treat them as such. And then we get into grounding and bonding, which I know is everybody's favorite, you know, topic, bringing up those questions and things like that. And so that becomes a definite part of that around meeting those grounding requirements as well, making sure everything's bonded properly, you know, your neutral ground bonds are being done properly and all those kinds of things. All right. So just kind of a you know, an image to kind of help drive this home, I think, a little bit more is, you know, talking about, again, this is that typical application. So now we have that 480 over there on the inverter side. We have the 208 on the utility side. And so using that delta to Y transformer in order to make that interconnection for those types of systems. This is the one that we're seeing the most often, and in this application, and you know, again, a delta to Y, and then getting those primary and secondary configurations or those designations down is kind of that important part. Not sure if Jeff or Nick, if you had anything you wanted to add on to those guys.
Anything jump off the page at you, Nick, there?
No, I think you're pretty spot on here. I think we kind of hammered home between primary, secondary, and the interconnection here with the transformer.
Okay, cool. So the kind of, not the last one, but you know, for our grid direct systems, we're going to move over to energy storage after this. But actually, a couple of questions came up, and I'm going to try and scroll through them as I kind of hand the slide over to Nick and Jeff. But can you guys talk about this bidirectional? We have that circled on this label here. So, you know, that being an important aspect of specifying these transformers for these applications. Can you guys kind of talk about what that means and, you know, why folks should be, you know, looking at that?
Sure. Just to cue this up real quick. So what we inserted here is this is a copy of the nameplate off of you know, what a standard 75 kVA solar duty rated unit that we have, and there's some things on there that are unique to the design of this unit that do make it suitable for solar duty, and that's one piece of it there. So anyway, Nick, you want to get into that a little bit on the bidirectional piece of it that's labeled there and circled?
Yeah, sure thing. So that's important from a design standpoint to say that, you know, it is suitable for power to run either directions. Some transformers can utilize a compensated winding, which to my understanding are only suitable for power flowing in the intended direction there. So you can't see, I believe, voltage loss when power is flowing back towards, say, that primary side there. Additionally, kind of on the nameplate here, you know, we do like to designate, I know inspectors do like to see which side of the transformer is designated as that grid side. So we make sure that we know for those inspectors say that both, hey, the transformer is suitable for this application. It's not being, you know, backfed, so to say, and to call it clearly, you know, how it's intended to be used here between grid and inverter side of the transformer.
Great. Yeah, and so this is one, I think, just as, you know, part of working with, as far as the engineering goes and the design and installation goes, working with the manufacturer, making sure that this is part of that spec is kind of the important part.
Yeah, and to emphasize too, it's important to have, you know, primary versus secondary specified correctly, because if you say flip the voltage on this one, then it would call out the high voltage side as the grid side, which then causes a direct conflict in the nameplate of the transformer and how you're using it there, which always puts kind of a tricky situation for people.
Okay. And is this, and in the introduction, Jeff, you mentioned dry type transformers, but is this bidirectional, this hold true for both oil field and dry type transformers? Is that something that people need to be thinking about?
Sure, it would be the same principle, whether it was oil filled or dry type, sure.
Okay. And I guess, a question came up, and it's an interesting thing, is so we're talking about these transformers that are, directly connected to our inverters, connected to our utility. What about on the utility side? Is this something, this bidirectional aspect, is that something that's, of concern, or how does that fall into this? Do you guys have any input on that?
Thoughts, Nick?
I would say, we would still comply with the utilities requirements there. It's more just visibility on the functionality of the unit here, I would say.
Okay. Great. Okay. We are just about right on time. So I wanted to make sure that we have plenty of time talking about with everybody, but kind of talking about some energy storage stuff as well. So at this point, Medina, I'll have you kind of take over on this and, kind of setting the stage. And so I think one of the first and foremost question is, and you have it right there at the very top, need for isolation transformers. And so, when we're talking about an energy storage system, I guess, what is it about the energy storage system that requires this isolation? And, is that on the power conversion system side? Is that on the load side? I guess if you can kind of address that, and then we can kind of go through some of these other main points when considering transformers for energy storage.
There are several reasons for the need for isolation transformers. Primary is galvanic isolation, and Jeff and Nick have touched on that. Basically, the Autotransformers are just continuous winding, so there is no isolation for galvanic isolation. The windings, primary and secondary windings, regardless of how many of primary and secondaries, have to be galvanically separated. So there is no contact between the two or between any windings within the transformer, regardless of those windings being in the same common magnetic field and actually performing the function as they are. It's still galvanic isolation. And that is in PV systems between the grid and the equipment, power conversion equipment. Again, as I said, several reasons. One being galvanic, the other safety compliance, then grid compatibility, noise reduction, grounding flexibility, equipment protection, limiting the overcurrent protection, and acting as a overcurrent limit in that point, in that function. So for galvanic, it will actually suppress any risk of ground faults, electrical shocks, any safety hazards, and it will also help protect sensitive equipment from transient voltages and spikes. The impedance of every transformer that is in there is actually acting as a blocking for any spikes going through. So the transformers with lower impedance will have a different inrush current, because impedance helps with inrush current. And there are sometimes transformers that are purposely designed to have very high impedance to suppress the inrush and also to suppress the harmonics. That impedance of the transformer will play a big role in there. So for safety compliance, in a lot of regions, utilities will require and the electrical codes will require to have that galvanic isolation. And in order to establish the compliance with standards, it will require the use of isolation transformers. For the same reason, it will be grid compatibilities that will actually be coming from the grids in terms of limiting harmonic distortion, any voltage fluctuations, and ability to actually put the proper protection on the transformers and put the meters on the transformers and make sure that no transients and nothing actually goes directly on the equipment. Noise reduction is also the same. And PV systems will sometimes, especially PV systems, will create a noise or be very sensitive to that noise if it's coming from the input side, and that gets suppressed and filtered through transformers. I'll grant you that there is a lot of noise and those transients that will go through the transformer, but it's much easier to capture them on the secondary sides, and there are also ways of capturing those transients and suppressing them so they don't transfer on the PV equipment and equipment that is behind the transformer, looking from actually the user point of view, not the grid point of view. The transformers, depending of the group of the transformer and configuration, will allow for additional grounding, flexibility for neutral connections, and creating and feeding those on the PV side. If there is 120, that would be required. So from 208, you can easily derive that. Grounding, flexibility to ground the system, because some of the utilities will require Y connection or Delta connection if they have grounding issues, and if the utility side is grounded, then they will require Y connection that will be grounded. That Y connection and grounding can also create a lot of issues on a PV side. Some inverters will have neutral, some will have neutral, grounded neutral, but in general, none of that. And if that neutral is grounded on a PV or a inverter and or a microgrid, that can create a lot of problems, because it closes the ground loop and provides a path for return current that can be quite high. So that becomes a problem. And as I mentioned previously, it's equipment protection that is very important, and the transformer with its presence and its role plays a big role in that protection, allows for a proper protection, proper reading, and proper suppression of any transients and problems that may happen in between the grid and the PV and solar systems.
So so I guess kind of touching on that last piece of yours, trying to understand that a little bit better. So what are those, I guess, what are those problems, or what are the potential noise issues that you were referring to that could come back? And is that on the energy storage inverter itself specifically?
Yes, on energy storage inverters that can come back if the ground loop is closed, and there is a lot of fluctuating currents that can come back. That can create a lot of problem with sensitive electronics and controls, and we have experienced that firsthand.
Okay, so within the energy storage inverter itself,
Yes,
seeing those coming back to it is causing problems, and then either creating whatever issues shutting down or anything like that. Very interesting.
That's correct. I'm just looking at the slide, and I purposely put harmonic distortion and voltage fluctuations there. And I'll go back to where my expertise lies. Those are the large industrial systems that we have, depending on the transformer and rectification elements and groups and the number of pulses that the rectifier is supplying on the DC end. That harmonic distortion can be very, very high. Transformers with its impedance can act a big part and have a big role in harmonic distortion suppression. Impedance of the transformer, the group of the transformer that is selected, that dictates and allows the rectification elements. That plays a bigger role in just straight conversion when it comes to inverters, and when it comes to solar panels. Harmonic content is not very high, because the switching frequency of these inverters is much higher, so it basically does not allow generation of those harmonics. And I saw that somebody did ask what is the K factor for the transformer for these systems. It's usually 1. It's very low. And Nick and Jeff can confirm from the requests and from the transformers that they're building.
Yeah, that falls in line with what I normally see out there for requests coming in as well.
Yes. Yes, because the harmonics are really not high in those systems, and there is no harmonic distortion, almost none, compared to larger industrial systems, and how much is being put back in the grid from those systems. Something similar that you see in the picture, this was actually 54,000 amps rectifier IGBT system, 12 pulse, and the transformer on the front is oil field transformer with forced oil cooling.
Great. So I see there's a number of questions and something that came up earlier around Autotransformers. And Medina, this was something we talked about during our prep call. And everybody's, we talked about it with our prep call. But Medina, you had talked about specifically, you had seen, or maybe I wasn't clear if it was Dynapower specifically, but I had tried to implement some Autotransformers and things like that, and just they're not effective, not seeing them working properly. Can you kind of talk about the use of Autotransformers in general, and kind of what you saw specifically in those examples when you were using them?
Sure. Autotransformers are useful in some instances. If there is a need to step up or step down the voltage, or use different voltage levels in occasionally, autotransformers can be very useful. They're usually used as an adder to the main transformer. So isolation will be present there. For the main transformers, these oil field transformers are sometimes designed such that there are two transformers on the same core. And the reason for that would be, I'll just bring an example of 12 pulse rectification that requires a single primary input winding and requires two secondary windings. That's usually delta Y connection or delta YY connection. So in order to design such a transformer, especially on the high voltage, and if we add any offset to the primary windings, like 7.5 degrees with two transformers, such a transformers working in combination to provide 24 pulse systems, then in order to accomplish any voltage change and taps on the transformers, it can only be done by the use of auto transformer. So that would basically be one single winding on the core per phase with different taps to that winding. And if you, for the winding and for the transformer design, it's always volt per turn. So depending how many turns are in circuit, that many volts will be present in the circuit. So if you want to affect anything on the secondary voltage or to do primary voltage adjustment, then tap changers would be there, and taps. So if we have a combination of two transformers within the same tank, then the only way to vary any voltage and affect both transformers would be via auto transformers. So there is a perfect fine place to use auto transformers. In smaller systems, where we use them is when sometimes our customers have existing equipment, and they would, for whatever reason, the primary voltage for that equipment is not available or changes in the buildings. They would want to have some way of adjusting it to a different voltage. For example, if they had 480 volts rectification system, and now they have 240, we would provide auto transformer because it's much smaller size wise and still provides everything that's needed. Equipment still keeps its own main transformer. Auto transformer just provides that different voltage level, in which case isolation is not really needed. But to use auto transformer only without isolation transformer is definitely not recommended, because it's no isolation, no galvanic isolation. All transients and all problems that are coming from the grid will go directly to the equipment and will directly affect the equipment behind that auto transformer.
Thanks, Medina. I'll just add my experience with Autotransformers has really been in a backup power microgrid system where we're doing phase balancing on a split phase system. And in those applications, yeah, Autotransformers are pretty critical to meeting customers' expectations in terms of delivering the amount of power needed to service load.
Great, yeah, but yeah, not providing that isolation, kind of all this list of things here, they're not able to meet those needs. So perfect. Thank you for that explanation. Very helpful. So this was a good question that came up. I saw it kind of get a differentiation between the grid following versus grid forming inverters. So I think maybe we didn't talk about that in our prep call, so I'm hopefully not throwing everybody completely off when I kind of bring this up or we talk about this. So when we're talking about the energy storage inverter, so we're actually showing in this image, we're actually showing a PV system with the grid, a typical grid following inverter, just a grid direct inverter. And then also showing, in some cases, we're seeing energy storage inverters that are doing the same thing. They're grid following, they're there for grid services only. And the need for a transformer, I guess Medina and Nick and Jeff and Blair, to throw this at all of you, kind of just talking about I guess that need for that transformer, in this grid following versus in the next slide, we'll talk about grid forming, where the battery inverter is actually forming the battery inverter is forming the sine wave and powering up backup loads. So I think is that a big differentiator in the eyes, and maybe I'll look at Medina and Dynapower first. This grid following versus grid forming and that transformer requirement. My question.
Yeah, it is a tricky question for me because of terminology.
Sure. So the grid direct inverters. So I guess kind of where we were going with when we were talking about is we have these grid direct inverters, and in this image we're showing a grid direct inverter doing exactly that, going directly to the utility without a transformer, versus a battery inverter needing to go through that transformer. So I think it's kind of getting into what you were talking about, the harmonics and all those issues, the need for that isolation, and I guess just trying to differentiate between the need for needing the transformer and not needing that transformer.
Right. Dynapower does actually offer grid-tied inverters, but also the inverters that will work with energy storage and battery storages and solar PV, and will also provide DC to DC conversion systems that will allow direct solar PV directly feeding the battery and vice versa. So grid following inverters do not require the transformers because they're directly on the grid, and those solar PV systems will have to be compatible to the grids and grid requirements, and they go through all kinds of verifications, testing, and certifications. While with the energy storage and presence of batteries, especially battery storages, that transformation is crucial to protect both battery storage as well as protect the grid from unexpected battery storage and energy releases back on the grid. That's mainly that isolation where it plays the role because of that storage presence. If there is a solar PV inverter that is directly feeding the grid and working with the grid, it is okay. If there is a storage present, then there is always a possibility of unexpected energy release and any transients and problems going back directly to the grid. So that's where the transformer and isolation plays a big role.
I think it also comes down to the fact that solar is just inherently current limiting, unlike energy storage.
Yes.
Yeah, that's a great point. I hadn't really considered that one, Blair. So I mean, so this next image is very, very similar to that last one, but in this case, this was all doing the DC coupling, and so again, really, I think the same concepts of what you were just speaking to there, Medina. Just now we are putting all of the DC sources over there on the DC side, and then using a single inverter in order to be able to both follow or be a grid following or grid forming inverter. And so having those needs around that transformer there.
Yeah, that is correct. And we do have our DC to DC conversion that is actually patented, I believe, for Dynapower. Blair, correct me if I'm wrong. That is a version that will allow us to do communication and energy transfer back to the grid, but also have a battery storage and have a PV solar to work through that inverter back to the grid, and also work directly into the battery, and also battery back too. Because sometimes lately, actually, the voltages on those battery storages have been going up, and we've seen a lot of requirements for 800 volts, and the DC voltage from a PV not necessarily has to be on the same level. So there is a need for that DC to DC coupling and DC conversion system, DC to DC.
Great. So there's a number of questions here, and I'm going to see if I can kind of queue some of them up. If on the panel, if there's questions that you see that you want to definitely get to, we've got about 8 minutes or so here. And this is great. I want to try and get through some of these questions. One of the ones I wanted to throw out first, and I think Nick or Jeff, you might have been typing out an answer, but I wanted to bring it up to the group because I think it's a good one. Asking about bidirectional inverters. And so the question is from Matt saying, what physical parts are modified to help power flow bidirectionally? Are the units actually built differently? So I guess that would be a question. Is there something physically different about the transformers when we're talking about the bidirectional?
For the most part, not necessarily. A lot of it comes down to the engineering time and the testing to ensure that you don't have any voltage drop or imbalance there when you're running power in either direction there. For the most part, it is physically the same. It just comes down to a lot of the testing, the proving that, hey, this device will function as intended when running power either way.
Okay, great. Another question that came in, so kind of going backwards, talking about towards the beginning there when we were talking about delta Y configurations, and the question came up, do we ever see delta delta configurations given that PV inverter? So again, talking about grid direct PV systems, we're not talking about energy storage at this point, but the grid direct PV systems, since a lot of inverters don't require the neutral as an absolute, do we see delta delta? And one of the things we have to also consider is, so my answer and I'm going to look to the group to refute, or I'm going to say no, but I'm going to look to the group to see if there's like anything that I'm missing here. But one of the big things here is around the ground fault protection. And so if we are putting the delta on the PV side, then we're going to have to actually add a way of doing some ground fault protection, because there's not that neutral reference, there's not that ground reference. And so having the Y on the PV side is an absolute requirement because of having that reference and being able to use the ground fault protection schemes in those inverters and making sure that they're working properly. Kind of look into the group here to if there's anything that you have to say about that one. Yeah,
that aligns with what I typically see there. Functional inverters might not require the neutral. I know a lot of them like to see that balanced phase to ground reference. If for whatever reason the inverter doesn't need that balanced phase to ground, you can still use a delta Y transfer and just not utilize the neutral. I mean, of course, you can go with a delta delta, but in terms of, say, product availability, the most common vector combination we have is going to be a delta grid side with a Y neutral inverter side. So no harm, again, not utilizing the neutral. It's just you're going to have more product availability sticking to that delta Y neutral instead of just an outright a delta delta. I guess the only caveat is going to be if you're looking, well, no, actually with the neutral always being the inverter, it doesn't matter if it's a 240 delta system or a 208, regardless, it's just best to have that neutral on the secondary side for product availability. Yeah, and that was actually another kind of a lead-in. Well, that leads into another question that I was thinking of, is product availability, and just kind of talking about these different configurations. Are delta Ys kind of the most common thing? So as we all know,
transformers have a long lead time these days, and so obviously we want to try and make those as short as possible, but not having to special order transformers would be another reason, I guess, on that.
Yeah, definitely. So most common is definitely going to be the Delta to the Y. There's also like YYs will be in stock as well. A little more limited, but definitely still in stock for many of the voltage, standard voltage combinations are running to like a 208 grid or 480 Y inverter, or just strictly 480 to 480 for the isolation there.
Great. Trying to scroll through here. I guess want to make sure that there's questions at the group here if you've seen that you want to make sure that you can answer. And I guess this was a question that came up that I'm not sure how quickly or easily we can answer this one. I'll give it a shot. But configuration, transformer configuration on phase loss testing, is that something that the transformer configuration has any impact on? When we're doing those phase loss testing, is that something you guys have seen?
I have seen when people are doing a phase loss test where the transformer, while being energized by two legs, will still prop up that third leg. Just so with it being a 3-limb core design, it does try to prop that up. Oftentimes, what I've seen or heard of as a solution for that is some kind of breaker that could take all 3 phases offline. I think something like an SEL 751 in the mix I've seen before. Those are usually the most 2 common things to just take all 3 phases off of it, because there are times, yes, where the transformer will prop up that phase there, even under a phase loss test.
Great.
Yeah, our equipment usually provides phase loss monitoring, which are fairly small and inexpensive devices that we would add to our equipment to sense the phase loss and trip the corresponding device, whether that being breaker or contactor, to disconnect the system and not allow it to work unbalanced. Also, the electronics will do the sensing and make sure that all 3 phases on the transformers are present. So that's part of normal protection of power conversion systems, embedded in the power conversion system.
Okay. Another question that came up was around sizing of the inverters. And so talking about inverters that have apparent output power and real output power, how should we be looking at those when we're comparing those to transformers? I feel like the short answer, what we've been doing, and I think this is appropriate enough, is looking at the kilowatt rating of the inverters and comparing that to the kVA rating of the transformers and calling it a 1-to-1. I think that's even kind of what we talked about in the early calls, Nick. So yeah, is there anything that we need to consider when we're looking at those different types of the power outputs?
No, for all intents and purposes, we usually just assume 1-to-1 with the kilowatt to kVA for sizing there. I mean, obviously, it'll never hurt to put in a buffer on the transformer. When it comes to most transformer efficiency for DOE 2016, peak efficiency actually is at 35% load, and then it slowly does taper off as you approach 100%. It's not an egregious amount of efficiency loss at 35 versus 100%, but you can actually have some cost savings too if you do, say, oversize from, say, like a 112 to a 150, and you aren't constantly loading at 100%. There is a little kickback there for watt losses on the transformer.
Perfect.
But these transformers are rated for continuous duty, right? I think that's
Yeah,
part of the,
exactly.
yeah.
They can do 100% continuous if needed.
Yep. Cool.
Yeah, and I think that's again, going back to our prep calls, that I think that's one of the things that us and the when we're doing all of our electrical calculations and things, we've gotten so used to a 25% safety factor on just about everything. I think people maybe start to think and start to apply that to the transformers as well. But that was a great thing to put out there, just noting that they are 100% rated, and so we don't have to have these like built-in safety, or we don't have to put in safety factors of 75% or 25% less or something like that.
Yeah, unlike gas circuit protection, you got it.
Exactly. Yeah, we get quite used to that, doing that for fusing and wire sizing and things like that. Well, great. Well, we're coming up to the top of the hour. I really appreciate everybody's time. I wanted to make sure that we did get folks' contact information up here. I tried to address at least kind of going through the common themes on the questions. If there's additional questions you have, welcome to reach out to us directly at Mayfield Renewables. Happy to talk about it. This is a pretty big topic. If there's more we need to dive into in future episodes, would love to do that. Invite the folks back on the panel. So I really appreciate everybody's time that you have to spend with us. And then a last couple things, we have additional classes. I mentioned this kind of during the course of it. We have, talking about codes and standards, National Electrical Code. When we get into overcurrent protection, wire sizing, disconnects, those kinds of things, we do cover that in our full code class. And then we have a number of other classes available for folks on our website. Happy to have you take a look at those and see if that's something that you'd be interested in participating in. And then finally, next month, just save the date, a plug, we're going to be talking about large scale solar design with string inverters. And so going to be, kind of diving into that. So would love to have you join us for that as well. If there's questions about that topic, as always, happy to have you send those ahead of time. So as we're closing up, Medina and Jeff and Nick and Blair, I really appreciate you taking the time and joining us and, helping give some more of that information about the transformers. And again, I think it's very helpful for everybody to participate.
Thank you, Ryan. This was great discussion. I'm grateful for your invitation and hope to participate in these seminars again.
Yeah, we appreciate it from the Hammond Power Solutions side on behalf of Nick and myself that we're glad to be a part of this and appreciate everyone's time today.
Great. Thank you all. I appreciate it. And hopefully we'll see you at the next AMA.
Thank you.